This conference will now be recorded.
Okay, everybody, again, welcome to the OCP HPC sub-project call. This is March the 9th, 2021. So looking at our agenda, I'm sharing the screen at the moment. So our agenda at the moment, got introduction to new attendees. I don't see any at this particular point in time. So we'll move on from that topic. Philippe is kindly just going to give us a little bit of an update on some of the other activities that are going on from the thermal management perspective across OCP specifically. Because obviously I think that's going to be an important aspect of what we're doing, and whether we can jive with everyone else or maybe come up with some other ideas we may see. So Philippe, would you like to just give us a kickoff?
Yeah, sure. This is a verbal update, and if the team here wants more details, then I can come back at the next meeting with more information. I think the biggest influence on high power computing, high performance computing would be the OCP initiative to bring liquid all the way to the rack. This is in the advanced cooling facilities work group, and they are defining the path to bring facility liquid in a standardized fashion to every rack. So this would then enable heat extraction through hot liquid instead of hot air. Any questions or interest on this one?
Yes, that's good that they're actually going to bring it to the rack. So that's so yep. Fundamentally it's going to be available at the rack itself.
Yeah, and so there's quite a bit of effort to define a standard way to plan that, like at the facility level, including all the facility level modeling systems, which is called a BIM, a building integration model, I guess. And all the way down to choosing the size of pipes and connector types at the rack level. Now, this advanced cooling facility group is creating subgroups. There will be a subgroup, which I'm a part of, that will define in detail the interface between the facility level pipe and the rear door heat exchanger, which brings me to my second topic on the OCP community, which is the rack level thermal management stuff. So if there's no further questions on the facility level stuff, we can skip that and I can move on to the next one.
So you mentioned rear door heat exchanger. So is that just one option, or is that going to be part of the main?
All right. So yeah. So now that we get into the rack level stuff, there is the Open Rack version 3, of course, that is the new rack, and it has now an option to have an RPU, a pumping unit, to circulate liquid within the rack. There has been a definition of a manifold to, it's like a liquid bus bar that runs along the back of the rack from top to bottom, and brings cool liquid to each server and extracts hot liquid from each server connected to the pump. And then the pump has two options. It can dump the heat from the hot liquid into a rear door heat exchanger and give the heat back to the facility in the form of hot air. And so that is for the existing facilities that do not have liquid brought to the rack. Or later on, the pumping unit can exchange the heat directly with the facility liquid. that if it is available at the rack level.
Yeah, okay,
So,
that makes sense.
so
Okay.
there is a completely separate group that defines the usefulness and function and specs for the rear door heat exchanger. There is a separate group that manages the design and the spec of the manifold, its location in the open rack V3, type of blind mate connector, and things like that. So if we are thinking of designing high performance compute servers that connect into or mount into the open rack V3, and if you want them to be liquid cooled, then it would be good to get connected with that spec so that you know how to design the back of the chassis. I have to also mention that rear door heat exchanger. Right now, the team is contemplating using it as a way to extract the heat from hot liquid that is collected from the servers. But there is also another option later on to collect the remaining heat. So let's say all the servers are liquid cooled, but there are a few components in the server that are not, like hard drives or drives. Then there could be an option for the rear door heat exchanger to be an extractor of heat from hot air.
So like a
into
radiator
liquid.
in your car then, basically.
Sorry?
A radiator in your car sort of effect. Huh?
The other way around, more like an air conditioner that collects the heat and dumps it into the liquid, which the pumping unit would then give back to the facility water.
Okay, so you could have a mixed. Your server could be mixed, partly liquid cooled for the hot ones and air cooled for the cooler devices.
Yeah, they need to be, but the rear door heat exchanger needs to run in only one of the two modes. Either it dumps a lot of heat from all the CPUs into the facility air, or if there's facility level water available at the rack level, then the rear door heat exchanger can be used as quote unquote an air conditioner for the rack to keep the.
So you couldn't have a hybrid mode if you had liquid at the rack. Could you not have a possibility of a liquid exchange for the hot devices and
That's right.
the air cooled for the others? So you have like a hybrid backdoor cooler.
That's exact. Yeah, that's what I'm trying to describe.
Okay, perfect. Yeah. Oh, excellent.
Yeah. So that is the rack level effort. So are there questions from the team on this one, or requests for more information? So there are two completely separate tracks for this. I imagine that this group, if it intends to create a spec for high performance compute sleds or servers, then the main area of interest would be the manifold, the ORV3 manifold. And then at the node level, I am only aware of one liquid cooling initiative for the Open Accelerator platform. So there was a reveal, I don't know, within the last 4 weeks of a spec for an air-cooled Open Accelerator platform. But a new program has started to put in place a liquid-cooled Open Accelerator platform. And should I expand on what the Open Accelerator platform is, or is everybody on the call?
Well, actually, I do have a slide on that in some of my upcoming ones, but yes, it's is where the big high power accelerators go, right? So the modules are currently 700 watts, and they go all the way up to they're proposing that in version 2 they go up to a kilowatt per module. So we definitely need liquid cooling to cool those, right? So.
And there's 8 of them in one box. Right now the box is very tall. So this this will require a different approach to liquid cooling inside the node. That's going to be interesting. Traditionally, liquid cooling inside the node is more or less a fixed configuration that allows for some maintenance, but not really a diverse mix of chips. And by definition, the Open Accelerator platform allows a mix of different modules, like different applications, different brands, different chips. So in order to be able to accommodate that, inside the node, there will need to be a manifold and quick disconnect system to allow the insertion and removal of open accelerators, well, chips, and to allow their cooling. So that is brand new. It is just starting, and that is the only thing I'm aware of that I've been involved with anyway at the node level.
Yeah, I got a picture of that in my slides actually, so that's good.
And that is my update of what I've learned. There is a cold plate. There was a cold plate group, but I joined too late, and I think it is sort of winding down its work.
So what's that? Is it decided it wasn't a good idea, or?
I think the work is done. I think liquid cold plates are kind of an old thing, so I presume that the spec is complete and that
And that's what
understands what
OAI
needs
is
to be done.
Right? That's the term for what OAI is using. Is that correct?
Sorry,
is that the term is liquid cold plate what the OAI solution is using, or
the OAI, yes, will need liquid cold plates for every chip, and I think those are easy to define. The challenge will be to define a way to connect the liquid cold plates to the manifold, define the manifold inside the chassis, and define a way to be able to connect and disconnect those manifolds. Traditionally, they're hard connected into a very long loop that gets assembled at the integration when the system or the node is integrated and never touched again. But this needs to be field configurable, for lack of a better term.
Right. Okay. Well, thank you, Philippe. That was useful. Any questions from anybody?
Does anybody have better information that they can correct me, please?
I think certainly the OCP is a wonderful labyrinth of wonderful little things that are going on, and sometimes they can be challenging to find. But if you are interested, then all the information should be available. I can possibly help, or Archon or Michael can help, and make, especially on the thermal side, Philippe might be able to point you in the right direction as well. So feel free to reach out to us if you want more info on that. Thank you, Philippe, again. I'll take over from here. So I'll just play my presentation. Can you read this? You see my slide? Anybody?
Yeah, we do.
Okay, great. So yeah, there was a couple of there was one conference and one little workshop that I went to. So there was a heterogeneous integration roadmap, which is a government-funded initiative that's been going on for a number of years, and so that there was a talk where they went into the metrics, and a lot of this is shrinking things down to the chiplet level, but you know they're relevant to us. And so I thought that was good. From Jar's input a few weeks ago on, we don't want to pump more kilowatts in the rack. I think Philippe has just identified that's exactly what we are doing. We've got 8 kilowatts now in OAI box, and we're trying to shrink it down from 3U to 1U with liquid cooled. So these things are becoming more and more challenging. So we do have to deal with more power, but it's a wrong metric to just do by itself, because we need to be massively improving efficiency as well as being able to cope with more power. I realize the metrics are still in definition. I don't want to get too tied up with them, but I would like to also try and move the ball forward so we know what we're measuring ourselves against. So this was a little bit more input. And again, these are the spreadsheets available online for you guys to jump in and put your own thoughts in. And so please do that. So this is one from the 4th annual symposium on heterogeneous integration, and from this particular talk from Professor Subhashi Mitra. The chart on the left is basically saying that, you know, the drive of computing right now is all about the energy times the execution time is the metric. So, you know, it says you can burn a lot more energy and actually get faster execution. But the idea is, or you can burn really low power, and as long as you're prepared to wait longer. And so it's a balance of, is there ways to get both of these? So I think that's what we're trying to achieve with this HPC, is can we get to this space of energy times execution time? And the other thing that he brought up was we've got abundant data applications, and the slide on the right. And he said he purposely didn't put any scales on this because he thinks it's appropriate whether you talk about power, capacity, or whatever. But he's saying it's a 95% memory problem and not compute anymore, guys. You know, so we need to cater for the memory side, the storage side, as much as we need to cater for the processor side, if not more. And he's talking about this obviously from a chiplet level again, a 3D stacking, and a lot of this really low level integration. So, but he's being brain inspired here. You know, it's the compute and the memory. It's all about the dense connectivity and energy efficiency. So I think these are, whilst these don't necessarily give us our metrics, I think they're, so I'd encourage you to listen to his talk. It's really quite an interesting talk. And how could we use this in our efforts here in the HPC sub-project? The other presentation was from a chap called Brad McCready. He used to be a very senior VP in IBM for many years, but he moved across to AMD recently. And he was given a presentation on high performance computing and the needs of it as we go forward, and a couple of interesting charts. Again, he was this chart in the top left was really talking about where we've come from. We've come from dollars per megahertz, gone to then we progressed to dollars per thread performance, and then dollars per throughput performance. So it was all dollar driven. No mention of efficiency. And then those little red arrows are saying we need more and more innovations if we're going to keep the Moore's law curve going, you know, in terms of being able to use those doubling of transistors, etc. But then he shifted over to saying, look, it's a performance per watt. So the same as the previous presenter. This is where we're at today. It's all about the power. If we can't reduce the power, we can't get the performance. And obviously he's advertising AMD here, and he's showing what they've been doing on that front. And then finally, I thought was relevant to this is we need these heterogeneous accelerators. And he's shown here that, you know, general purpose processor is, you know, sitting in the middle, sort of balance between compute intense workloads and maybe things like pixel rendering. But you've got gaming optimized architectures for your GPU, and compute optimized architectures for that are similar to the GPUs, but like for the AI, etc. So he's beginning to separate these two out as to where AMD's going, whereas I guess the argument is NVIDIA's trying to mix the GPU and the compute optimized into one device. So he's accepting there's many heterogeneous accelerators going on here for the best HPC. So I thought these were good inputs to our metrics. I don't really want to necessarily discuss this more right now, but it was just to sort of try and get our heads moving in the direction on the metric side. I mean, does this jive with everybody? Is a general the core center of what we're trying to achieve with what we create in this sub project? Does anybody disagree with what I'm saying on this? I mean, if you're all in violent agreement, fantastic.
Yeah, Alan, I'm, here again, you guys, the crowd here is definitely more akin to this kind of stuff than I am. But I'm still trying to work through and where the HPC group is going to crack out or have its niche. Certainly we're getting good presentations across the different niches across OCP and things, and so and we have to be guided by that. Hey, power is important. Absolutely, those kind of things. I think this is very wise and setting the stage. And I heard some things about maybe how, part of the scoping is going to be the metrics, defining metrics and things. So I don't know. I kind of I'm kind of still there. I want to dig into something, but I don't know what to dig into yet.
Yeah, hopefully, Gus. That's good point. I mean, yeah, we've got to find our space, to your point, our niche, right? And that's what I'm trying to do here. We've got to remember this work group. You've got the big powerhouses of the silicon powerhouses that are making these wonderful devices, and really what we're doing as a standards body is we're trying to make all of these wonderful innovations accessible to the high performance computing community in a consumable form. I think that's my simplistic, and hopefully the following slides will start to color that in. That's why I wanted to get on the following slides. I've been introducing this modularity, flexibility, and composability. It is a core tenet of OCP is modularity, and it's what can we do at an HPC level, because if we look at what's going on across the rest of OCP, sure, they're doing lots and lots of modularity, but there's less concern for the needs of the HPC. So if you like, the HPC is the Formula One of the computing industry, and they don't need to do that with a lot of their standard sort of server architectures, and arguably we're trying to do it in the OAI chassis. But again, we're just looking at accelerators there. We're not looking at the whole HPC compute problem. And so that's what I'm trying to introduce here. I think that, and we are a hardware focused organization, but we have tentacles into the software. So we need to make sure the infrastructure is good for the software to be able to use this. And ideally, any software stack should be able to utilize what we build if you put the hardware together in a recognizable way to a software stack. So that's the sort of generic of what I'm trying to achieve here. Does that make sense?
Yeah, it does, Alan. Thanks for. I keep on hammering those details into me, or that stuff. I mean, the direction, because I'd love to just have. I'm trying to write down my top 3 here, right? And maybe your presentations, your next slide deck is going to help me out. But I'm really trying to write down the top 3 and say, okay, now I got the top 3, and in my top 3 might be different than somebody else's, and that's okay. But out of these top 3, this is the ones I want to focus on and contribute. That's where I'm trying to get to. So. I feel like I'm not doing much good here right now.
No. This is good stuff. Getting ourselves on the same page needs these questions and the clarification, because and as we are all sort of feeling our way in the dark here, it's a case of, are we going down blind avenues or not? So everybody, please, thanks Gus, and everybody, please feel free to, if you sat in a corner scratching your head, ask a dumb question. I mean, I've made my life out of asking dumb questions, and when you ask a dumb question, you realize that 50% of the audience also didn't understand, but they were too scared to ask a dumb question and looked like they were dumb. So that's my career.
Yeah, Alan and team, don't get me wrong. I really appreciate the grounding that's going on here with the thermal discussions and the power per watt. Bringing in these influences into here, so we all kind of coalesce with a similar background. I think this is important too. No doubt about it.
Yeah. So in inviting people in, like last week, I thought that was quite useful to see the purchaser. The people that are spending the money are saying it's all about efficiency, guys. If you're not going to sell your system if you don't deal with this side of the. So it's interesting to get a procurement perspective there as well. So, okay, no, but that's great. Thanks, Gus. So I'll just move forward then to the next part of. Hang on a minute. Again, get my bearings again on my. There we go. Okay, so in the last few weeks, I guess we've touched on the modularity side of things and what's going on inside OCP. And we've got the OAM, the Open Accelerator Module efforts, and we've got the adoption of this. I've genericized it to EDSFF, which is the Enterprise and Data Center Small Form Factors, which is sort of proliferated into an interconnect standard called the TA-1002 that seems to be being adopted across the compute industry as a new pluggable format for all different devices. So I would like to just further my thoughts on that and see how this jives with everybody. So first of all, modular, flexible, and composable for HPC. Why? Well, technology's shrinking, but the computer architecture isn't. Chiplet technology is really, there's a hell of a lot of work going on in chiplets, absolutely masses of money, and the ODSA work group is doing a fantastic job of all of that. But we've gone from one extreme to the other in my simple mind. So the majority, and we all know that the majority of power consumption is in data movement. And it's not the compute, it's the data movement. Yeah, I've shown a picture of a classic server here. And if we just plot, we're constrained by this 19-inch rack. And if we just plot the units on here, you can see the storage at one end, the I/O at the other, the compute in the middle with the memory closest to the compute. So we've got this massive space and we're constrained by that today. If you look at, we're doing sleds now, but the sleds still have storage in the middle, compute in memory, so storage at the front, compute in memory, and then I/O at the back or whatever similarity. So we're seeing that the node volume is in the region of 800 cubic inches. The node interconnect needs to be in the region of 5 to 10 picojoules per bit to get across these motherboards into the I/O or storage or whatever. And our option is that we're trying to innovate like crazy into the chiplet world and go into the like quarter or 0.1 of a picojoule per bit, you know. So we're really going from one extreme to the other. Well, fantastic if we can get to that chiplet world overnight, but really going 100% chiplets on a substrate doesn't answer the flexible part that we need. You can't quickly take a couple of $10 components and plug them together in a chiplet. You've got to spend $1 million to get the packaging done right to get it into production. So you'd better have a big opportunity. We need some level of flexibility in this modular and composable. So chiplets give us modularity, chiplets give us composability, chiplets don't give us flexibility when they're put on a same substrate. That's the problem that I see. So we really need easy disaggregation and easy composability. That's what's required. So my question is there a middle ground? So, i.e., could we somehow pack those elements into a nice cube? Could we get the node volume down to less than 200 cubic inches as an example number? Could we get the node interconnect to around about a picojoule per bit? So maybe, you know, 5 to 10x improvement on what we've got today. Obviously nowhere near as good as where the chiplets, where they're 1 millimeter apart, can get, but a 10x improvement still feels like a good step forward. And by the way, that doesn't preclude us having to use chiplets. Chiplets can reside on each one of these blocks, on any or all of them, and so we can still leverage the beauty of chiplets, but we try to retain some of the flexibility and pluggability of these devices. So that's what I think we can do, and I think HPC's demands give us this potential opportunity. So this is a slide I updated slightly, but I showed you the other day, saying we've got some wonderful building blocks in OCP, and they come from OCP, JEDEC, and SNIA. This common EDSFA interconnect, and I categorize them into the less than 100 watt and 200 watts to a kilowatt with the OAM modules, the accelerator modules. And you can see I've got the little cartoon blocks to show we've got all those building block pieces, and they're already there. I can buy an SSD in E1.S from Samsung, from Kioxia, Toshiba originally. We've got OCP NIC-free. I can get NIC cards, glorious, with that connector. We've got JEDEC differential DIMMs. I can get differential DIMMs in that connector format. And we have cable I/O. We can do I/O on these tiny cables with the tiny PCBs. Maybe we could put NIC 4.0 could be a NIC inside that cable connector when we get to the chiplet level, or silicon photonics inside that cable connector. But we still need these really big, powerful CPUs and accelerators. So how do we bring them into the equation with these wonderful incompatibilities here? And again, chiplets can reside in each of these modules, multiple chiplets. So we're not precluding chiplets. So if we decide to re-architect, could we start with the cold plate? And Philippe, this is where I'd love your help for high wattage OAM modules. So let's look at this. This is what Philippe was talking about. There's the air-cooled version of the OAM module, and you can see below 8 of the OAM modules being water-cooled. So I think this is one of the early concepts of the water cooling for efforts in the OAI chassis. Okay, so we've got this work going on already. But couldn't we potentially, hang on a minute, could we potentially try and normalize, to Philippe's point, if we could get a heat spreader that you'd add to your particular module, where you had a capillary heat spreader where you could dissipate the core heat of the die across the entire area of the OAM module, so that you have a better thermal starting point on the module. And could we, instead of putting individual cold plates, could we make one ginormous cold plate with one pipe in and one pipe out, and we don't have these interconnect problems with our water cooling pipes, or the rat's nest that you see on the left? And because we have such huge power problems, we need to bring a kilowatt per module. That's 8 kilowatts, even at 54 volts. That's a huge amount of power. And we're concerned about the heating of the UBB motherboard to actually bring the power in through many 2-ounce copper planes and a very expensive PCB. So we could actually route the copper bus bars into the cold plate. So the cold plate serves several purposes. So you have a true liquid exchange going there, and you then you need a thermal interface, obviously, between the module and the cold plate. So the heat sinks are largest match. So this point here is I use an analogy quite often. Those of you that know me might have heard this before, but we've grown as our industry has progressed over the last 30 years. These heat sinks have become behemoths. And if I said to you, what do? Do you hang a picture on a wall, or do you hang your wall on a picture? You would obviously say, well, hang a picture on a wall. Well, why do we hang the wall on our pictures of our flimsy motherboards and our flimsy modules with those very delicate chips in silicon? Wouldn't it be better to hang that on the wall and the wall be the cold plate, not the other way around? So it seems obvious to me that we should be going with this approach. By the way, the military have used this type of cold plate for many, many years. So, and we'd integrate liquid cooling into this main cold plate, obviously. Then we could put 16 modules onto one, so we could use both sides of the cold plate, and we could double the density of the OAM here. The idea here would be that this would plug into the OAI chassis. So you see all of those interconnects being added. I'll get into a little bit more detail there, but we've got 16 OEMs mated either side of this wonderful cooling cold plate. So if we look at the OEM module interconnect, we need to get these TA1002 EDFs onto the module. So I'm showing the module here. And by the way, I've been doing quite a bit of work on these modules. So these are mechanically realistic. They're not the usual cartoons that I do. I've been doing a lot of effort to make sure this all works with the different modules. And the beauty of OCP is I can get these 3D models to actually play with for real, as well as the various suppliers. So I've got a connector on the top there. That's for mating between accelerators, interconnect between accelerators that are facing each other. So if you're thinking of like a 3D torus interconnect, then this would be useful, a 3D mesh. There's 22 connectors shown in the middle diagram. They're the 2C connectors, the by 8, and they could be for memory storage and I/O. That would give us 184 transceivers. If we use the 4C connectors and the 4C plus connectors, we could get a total of 312 transceivers on this module. By the way, those experts, and I'm sure I'm causing you all to freak out. That's the idea of innovation, so bear with me. So if we take these modules, we can populate anything into this setup. So going from the top left, that's an OCP NIC3 plugged in there. So by the way, we can mix and match these. I'm just showing them with just the one type. So we've got 8 OCP NIC3s plugged in. You can see we've got cabled I/O for interconnect between the modules, and or to the host interface board and or out of the OAI chassis. You've got the E3.S for the storage drives, the Gen Z type drives that have come from Dell and HP. And on the right, you've got the E1.S, which I believe has been adopted as well, or being adopted or talked about in OCP. And that's a sort of a replacement for the M.2, and you can buy drives from Samsung and Kioxia, etc. Bottom left is a memory version. So this is the OMI differential DIMM from JEDEC. So you can connect memory and DRAM. And by the way, the other modules can also have DRAM in them, obviously, if you want it. And then I've shown if you want lots of I/O, if you've got a problem that's not memory or storage bound, but all you want is I/O, we can interconnect with cables that can plug into the 4C or the 2C connectors, depending on the implementation. So we have, this really does, if you mentally join this gives us a complete set of composability. That ratio metric that I was talking about of flops to bytes per second to bytes of capacity, we can mix and match any of those to suit our application with this configuration. And we've got a complete server node inside a very small volume, is what we've got here. So, oh, my slides have gone out of order. Never mind. Oh no, that's right. So the module also, the other idea is that potentially the module could become the package. Cut out the middleman is what I've said. So one thing I've learned is that packaging dramatically affects power and signal integrity. It's quite scary that I've heard the number 5 dB of getting out the package for 112 gig. And then you go to solder bumps and then you solder it down. We used to have LGA sockets, but NVIDIA got rid of that with this module, this module approach, and we soldered it down. That improved things. But why have the solder bumps? Why not go straight from the die bump straight to a very high performance connector? So we would go path from die bump to die bump, could be of the order of around 2 inches or 50 millimeters with just one interconnect. And based on my efforts, my learnings from the ODSA, we could approach a picojoule per bit very easily with this type of interconnect. I know packaging experts out there are going to be saying the substrate that big, it'll never work. Yeah, all of this is not a slam dunk by any stretch of the imagination, but I think this is the opportunity for innovation, and this is what I'd like the HPC work group to be working on. Finally, putting it all together, this is just an example of a memory pooling example in an OAI chassis. So one of the big hyperscaler problems is they say they need memory pooling. OAI is only focused on acceleration for its name. Why not make the OAI the base chassis for the whole lot? So the modules could be CPUs, they could be accelerators, they could be Ethernet switches, they could be PCI switches, they can be, and then the modules can be memory, storage, storage class memory, and so we can populate this together. And this, we could make a wonderful memory pooling thing here. We could start with FPGAs or other modules. So basically, that's really the crazy concept. So I wanted to get you into thinking about that. So hopefully that gives us a better picture of where I'm trying to get our thought process going here. So on that note, I'll stop presenting. And so any initial reactions to that? Shock and awe, feel free to say, my God, what are you on, Alan? That's fine. or am I completely going down the wrong path here? I've shocked you into silence. Really? No comment?
I have maybe one comment.
Yeah.
Will there be anything we can say about the interconnect? So you've mentioned kind of power utilization, but would there be anything about performance? So particularly, say within a rack, within a chassis, and then outside of a chassis. So you have some kind of hop as kind of a unit of measurement, but we might want to make that more quantitative. I mean, maybe, yeah, just to be able to get some bounds or something. So not necessarily full topology information, but maybe something like latency for pings, assuming that there's no other interference.
Yeah, so a couple good questions there. So this is the sort of system architect that I'm looking at here, right? So by bringing all of these compute pieces together, if you look at the OAI chassis today, you will see that they've got retimers like confetti on the board, and this is even at 56 gig PAM4. And so that's just to get to the host, which is only literally a backplane connector away, or a coplanar connector away, or to get to another OAI box through the QDDs at the front. Everything needs retimers. Why? By going to this approach, we've got the cables. Now, cables are typically 5 to 10 times better performance than a PCB trace. So you've got a good opportunity there. And so therefore we can take, if we class a retimer as a hop, it's certainly burning power, then we can save power there by the close coupling of these pieces. And again, if you look at the application performance, Brad McCready was saying, you know, you need to mix and match these different compute nodes that would exist in the OAI type format, the OEM format. And so you could directly couple these together with very short links, or specifically build that, and you can build whether you need a lot of memory. If your application is memory bound, you can focus on the memory and just getting as much bandwidth into that processor with as much memory as possible. If you're IO bound, you can dedicate the IO to the IO. So you can actually, like if you had 2 accelerators and you really needed, and let's say you had 1600 gig channels, 100 gig times, you know, many lanes, and you wanted to connect those 2 together, you would normally go through a switch, but what you could potentially do is you could potentially just do a bunch of cables between the 2 modules, and say, I know my application always needs an interstate freeway between these two accelerators. And I don't need to go up through the switch for my application. I just want the lowest power interconnect, the highest speed. You would get the lowest latency by avoiding going through the switch. You wouldn't burn unnecessary power. So in this world of domain-specific architectures built for particular applications that Hennessy and Patterson have been pushing, you could make the really, really low latency, really high bandwidth interconnect between two modules and not go for the unnecessary top-of-rack network. But if you wanted to keep the classic top-of-rack network, nothing is stopping you from doing that either. And so that's what this composability and flexibility is really bringing us, if that makes sense. Does that answer your question?
Yeah,
No?
thank you.
Okay.
Hey, Alan, thank you for sharing those concepts. Yeah, so I'm wondering more like from, I don't know, like how to further work on this idea point of view. How do you see, or maybe you want to learn your suggestion in terms of how do you want to, I don't know, circulate or like realizing this? Do you think there is anything I may help in the OAI area? Or you think we want to make this a bit more mature here, hearing more from this group before? Yeah.
That's a very good question, though, Jar. And I think that this is clearly a lot of very radical innovation concepts which need us to break down the silos, right? If we can't work across the silos of the various different expertise in the different companies, from silicon to packaging to interconnect to, you know, to media, storage and memory, we are not going to be able to make this happen. And this is very much, it's very easy for anybody, any expert to say, oh my God, this is crazy, it's never going to work, right? Whereas if you look at the effort going on in OAI, for example, for OAM version 2, is very much an evolutionary path, and it makes a whole lot of sense that is the direction for OAM version 2. So I really feel as though this is more of a, why can't we change the world? Why don't we have a go? Why don't we do some proof of concepts? Look, why don't we write some white papers? I mean, if we could get a white paper going around. So I'm trying to stimulate thought with this presentation. This, maybe what we end up with doesn't look anything like this at all. It's what I've been working on for many years in terms of this type of thing. And it's the way I see it, but you know, I realize I don't necessarily see everything correctly. So if we can say, well, chiplets are fantastic, and it's the way the industry is going, but there'll only be 3 companies in the world that can make these things because they're so damned expensive, and nobody can use it. And we end up, our democracy of our industry is gone. And it's a case of, you know, me as a systems engineer, my building block will be an iPhone, is what I'm going to have to use to build any products. So, you know, and OCP is about standardization, and standardization is about enabling everybody, the tier 2s and the tier 3s. The tier 1s don't need enabling. They'll do it themselves their own way when they realize they're hitting $1 billion market. And I thought that's what OCP is about. So I'm thinking this is almost like the R&D lab, the Formula 1 lab of OCP. And if we strike gold somewhere with a piece of the concepts, then OAI could say, oh my God, that's a fantastic piece of what they're doing. I don't like 90%, but that 10% is great. And the OAI group says, we'll pick that up from OCP and integrate it into our OAI chassis. Or the chiplet guys will say, you know, that's a quite good use of our chiplets. Let's pick that up for our chiplet efforts. So I almost feel as though we're a bit of a systems prototype. Like if those people that know GE Global Research, the good old days of GE, their global research was a fantastic innovation engine they would come up with some major ideas, and then the big GE companies like the power systems division or the jet engine division or the medical device division, they would pull the research out of GE and use it. I'm trying to do that in an open community here, is the way I see it. Does that make sense, John?
Yeah, thank you. Yeah.
And these are crazy ideas, and they may be too crazy and completely unviable. I've heard a lot of challenges against what I'm trying to do here, and you know, and likely we try and they fail. But if we don't try and then we don't fail, then there's one guarantee: we won't get there. So that's what I'd like this group to become, and so I'm hoping that I can involve more of you. We can get more of a movement going here. Archana, I'm not sure if Archana's still on. No, she isn't. But Owen, you Joao, you were saying, can we write a blog out there? So I'm trying to get myself to a blog here where we can write this and we can maybe advertise it to get a bit more of a recruitment coming in to help us do this, because we're going to need experts. We need the experts in all of the disciplines, and we need collaboration across the disciplines for this to work, is my view. Any other inputs?
Alan, I like the innovation of this. I'm trying to understand the thermal transfer path, though. If the cold plate is the kind of the central, what we might have once looked at as a motherboard, I guess, or the main board. How do you get the heat from the individual devices that are connected? I mean, does it transfer through the electrical connectors that?
Yeah, no. So right, good question, Scott. And by the way, that's exactly a very good question. But this is exactly it. I don't necessarily have all the answers. I have hunches, and I try to optimize. But obviously, the 1 kilowatt device on the OAI module itself, on the OEM module itself, is going directly to the cold plate. So that has its own dedicated thermal path, which is clearly needed. On the media side, you would be relying on air cooled. So that was where I was talking to Philippe about the hybrid exchanger. So typically the media devices are of the order, like the memories, for instance, the DDIMM, they're less than 5 watts, they're maybe 3 or 4 watts. Whereas an SSD again is going to be in the region of 10 watts. Now EDSFF does specify that you could go up to 70 watts for an E3.S, for example, or the E1.S can go up to 25 watts, but they have different heatsink designs. They're asymmetric heat sinks so that you can get the airflow through them to cool. So you would take up 2 slots if you really wanted to burn 25 watts in an E1 stick. And so therefore you'd lose some of your IO capability. So, and each one of these media could have near media accelerators in them as well, like some of them do. And so the idea would be that you would air cool the EDSFF side, the media side, and you would liquid cool the big kilowatt processor side. Does that make sense?
That does, yeah. I'm sure we still would have to have heat spreaders and such, but
yeah, no. And by the way, one critical problem is the way EDSFF is specified today. The airflow goes from top to bottom of the module. We would need the airflow to go from left to right of the module for this to work. So you need to get the EDSFF suppliers to supply heatsink versions of their devices with the fins going in the opposite direction. So that's one challenge we've had to overcome. But yeah, so we need a mass amount of thermal modeling. This would be one hell of a thermal brick. And maybe there are some liquid cooling attachments we could do to the modules as well. but I haven't got there yet, and mentally I want to keep it air based to begin with. I think we're good with air based. Whilst we're sub 25 in the 25 watt or less range, I think we're fine with air cooled on those modules.
But I think I do have one thought. I think for the HPC and AI applications we are looking at for the data center, most likely in 3 years, okay, we would not see the CPU with external DIMM for the HPC and AI application, because right now the HBM is, I would like to say, is so cheap, okay. And
yeah, I saw you posting that, didn't you? Yeah.
Yeah, right now it's almost like $7 per gigabyte. We are seeing the CPU. My reason is in next 3 years for the HPC and AI training application, the servers for this kind of application would not have the external DIMM. It will only use the HBM and use maybe the memory expansion as a pool. So the liquid cooling or air cooling has to consider this kind of the new CPUs for new servers, not just look at the existing like the CPUs using the DIMM as the main memory. Now, because we need the bandwidth, memory bandwidth for the
AI. Very good point, Jinshu. And so I think what you're really talking about there is the DRAM memory piece. So first of all, if we just go back to let me just reshare here. I can reshare. I can reshare this one. Can you see that? Yeah. So this one here, this chip that I've shown on the OEM module is the Ampere from NVIDIA with 6 HBMs on it. So you're absolutely right. These OEMs are definitely going to have HBM. They're going to be chiplet based. They're going to have all sorts of things on there, and that doesn't. This architecture doesn't stop everything you've just said happening. There is an argument that HPC needs HBM memory bandwidth, but at terabytes and petabyte depths. And so HBM is a problem, is you can empty the HBM with an accelerator and need more data in a couple of milliseconds. And then if you've got a slow infrastructure to refill everything back up, you're screwed on a lot of memory bound applications. So maybe the DRAM disappears altogether and we only have things like 3D Xpoint or NAND that has to connect. Or maybe some people want a lot more DRAM than HBM can give. So again, the flexibility allows every application to dictate, I'm happy with an HBM configuration, or I want an external DRAM configuration. Does that make sense?
Yeah, what we are showing is the OEM. Yeah, it's very common for the GPU, or we call the NPU, actually neural network processor, to use the HBM. But what I'm seeing right now is the CPU itself will go that way for high application.
Yeah, for sure. I can imagine that as well. But a lot of CPU applications need the balance of bandwidth and depth. And it's interesting you say that HBM is low cost, for sure. Oh, I'm sorry, I've realized we're going over time. Apologies, everybody. Getting carried away here. And we're losing people. So, but very good point, Jinshu. But I think what you're saying is supportable here, because as these modules, that's why we're supporting 1 kilowatt. As more and more chiplets go into one module, then we can still cool these chiplets potentially. So I don't think this is blocking what you're suggesting could happen.
Yeah, I think for our experience in the last, it looks like an industry typically have like a 4 gigabyte or like at most 8 gigabyte per core for the CPU. And also the CPU is acting like a advanced matrix multiplication engine and vector engine. it looks like maybe right now the accelerator are separate from the CPU, but the CPU itself are acting more and more accelerator.
Yeah, no, for sure, absolutely. Yeah, I completely agree. I mean, whether we end up with a homogeneous world again in 10 years, I don't know, but yeah, it's a possibility. But at the moment, we're going out very heterogeneous right now. But yes.
Yeah.
Okay, we better leave it there. Thanks, everybody. Be good to continue the debate. So next week, on the next meeting, perhaps we can start to put some more meat on this and see if we can create a white paper or something like that. I think maybe the next step.
Yeah. Okay.
And bring up these issues. So thanks all. Much appreciated for your time.
Thank you, Alan.
Thank you. Bye.